Good afternoon, everyone. Thank you so much for joining us for our Storm Tech, the tools behind the forecast webinar. Today, we will be talking about Doppler radar. We have two National Weather Service meteorologists here with us today, Ms. Latrice Maxie and Mr. Eric Carpenter. And they're going to explore the basics of radar technology in meteorology, including how radar detects atmospheric phenomena. And we will also explore Doppler and dual polarization radar systems and discuss how meteorologists use data like reflectivity and velocity to track storms. They will also highlight some recent advancements in radar technology and the impacts on improving weather forecasts. So this webinar has an accompanying document. Is kind of like a text version of what this webinar will cover, and that can be found on the Mississippi Alabama Sea Grant VORTEX-SE page. I'll drop the link in the chat in just a moment. You can go there to read it. This session will be recorded and shared with each registrant, as well as posted on the Mississippi Alabama Sea Grant YouTube channel. We will have time for Q&A towards the end of the webinar. And if any questions are not answered, we will try to get back to you via email, but hopefully we can get through all of them. So our speakers today, first we have Ms. Latrice Maxie. She has worked with the National Weather Service for 25 years, 2.5 of those years in San Antonio and the remaining time in Jackson. She has served as a journeyman forecaster for nearly 8 years before becoming an observing program leader in 2009. She is a class of 98 graduate of Jackson State University, where she studied meteorology. And we have Eric Carpenter. He is a senior meteorologist with the National Weather Service office in Jackson, Mississippi, where he has been since 1998. He began his career at the National Weather Service office in Bismarck, North Dakota in 1994, and his hometown is Savannah, Georgia. Through the years, his research interests have covered a wide variety of weather topics, including many related to radar meteorology. He has 30 plus years of radar experience and hope to share some of his knowledge with us today. All right, so again, I want to remind you, if you have any questions, there should be a Q&A box. If you leave that there, we'll address them during the Q&A session. And without further ado, Latrice, I'm going to pass it over to you.
So good afternoon, everybody. Again, my name is Latrice Maxie. I'm a meteorologist at the National Weather Service. So today we're going to try to, give you some basics on radar, give you a little bit of history of one of the most important tools that we use every day. Okay. So the radar, which stands for radio detecting and ranging, again, is one of the most significant, most useful tools that we use on a daily basis. It has introduced us to some really significant information that was not available to us before, which is critical in the forecasting process and helping us to serve our mission. So the U.S., North America, the U.S. specifically, has some of the most intense active weather in the world, actually, and we are prone to tornadoes and tropical systems and some of those things. And here across Mississippi and the Southeast U.S., we experience a lot of those significant weather systems. If you take a look at the maps up there, you'll see, kind of over the last 40 years or so, the cost related to those significant weather systems, again, have impacted a fair amount of the southern U.S.
Latrice,
yes.
Moment, we're not seeing your slides.
Sorry.
Oh, it's no problem. There you go.
Okay, sorry. Sorry about that. So the little bit of talking that I've done was directly related to these slides right here. So you can see that billions of dollars um, are, occurred each year directly related to weather. And so having tools like the radar help us keep people safe and in the forecast process. So to give you a little bit of the beginning of the radar, um, a lot of people think that it's relatively new modern technology, but the concepts related to radar have been around for over 100 years or so. Hertz proved that radio waves could be reflected and refracted, supporting the idea that um, radar technology was possible. So light waves and heat are forms of electromagnetic waves. And then when we move into the early 1900s, people started using electromagnetic waves to detect, objects. In the navigation community, they were using it to try to find ships in fog, probably for safety reasons, to, protect against, accidents or things that were, happening kind of around the shipyard. We move a little bit further in time. We move into the teens and the 20s. In the First World War or so, then we're using the technology for military purposes primarily, to find again other objects. As we're strategic planning and those kinds of things. So by the time we got into World War II, radar technology was a strategy. They were identifying, enemy aircraft and those kinds of things using this type of technology. It hadn't quite become useful for scientific purposes and for, useful, I should say, for weather purposes. Of course, it was science, quite yet. Um, and so they were using it to detect other aircraft, to try to create plans for attacks and those kinds of things. So in the process they noticed that there was rain on the radar, but they weren't using it necessarily for a forecast process. It was just kind of identifying things that would be in their way as they launched their attacks. And so as we move through the World War II, then the use for weather radar became necessary. Um, and so because then they could see things that they couldn't see before and help in the forecast process and identifying various weather types for planning purposes, and just to again help them see things that they weren't able to see before. um, you know um, the Midwest was already seen as Tornado Alley, but they didn't see those things until they were already upon them. So being able to detect things at a distance was key for uses for the radar. And with excess parts that came about from World War II, with the U.S. and Great Britain and all of these countries, adding radar technology to their aircraft, and now they didn't need them anymore. Then it kind of transitioned to use for climate studies and different things that related to weather and weather forecasting. So some of the greatest development in our radar technology happened between World War II and the early 80s. And some of that technology we're still actually using today with the 8AD. So things like rain and snow and hail are all things that we can, basically detect with radar. Um, and our ability to identify these things quickly and accurately help us do our jobs a lot better. Um, um, Sorry. So this is kind of the evolution of the radar. I know, sometimes you get to see on TV the old World War I black and white little images where you see the light shining or pulsing, and you can see the aircraft, in the distance. So we have, evolved from that, process, but that is really kind of how, weather radar began. So you can see some of the early radar images. This one on the far left is the 57 radar, which it was just reflectivity. So the early radar pretty much just shot out and it gave us an image back. And this is kind of what you would see. There was still a manual process to it. They had to, crank it and, track things by hand and do a lot of things that were manual. So the technology was there, but it wasn't, you know, super. Again, it gave us access to things that we couldn't see. Um, and so, we move into, the mid to early, kind of mid 60s, early 70s. And they supplemented the equipment, added a little more motorization to it, but it was still kind of clunky and old, and not as clear. I almost feel like the 57 images, look a little bit better than what you saw from the middle images, which would have come from the 74 radar. And then we move into what we are currently using, the 88D, which is still kind of old technology. It's, a good 30 plus years, almost 40 years old, that was implemented kind of in the late 80s into the mid 90s or so. And of course, there have been some adjustments to it, but we are still using technology that's, approximately about 40 years old. So this is a look at, the radars kind of across the country. And as you can see, the greatest concentration of those radars are in the southeast part, in the eastern part of the US, which is where we get some of the most extreme and intense weather and where we really need this type of coverage. Again, to help us see things that we were not able to see before. You can watch a landfall in a hurricane using the radar systems. We can see, tornadoes, kind of across the state of Mississippi because we have, various radars looking, at the area. So this, good network that we have is really key also to us being able to perform our jobs. And our primary, purpose is the protection of life and property. And so this radar technology is key to us doing that. It's really, helped advance us quite a bit having access to the radar data. And if you ever ride that Interstate 20, when you get into the Brandon area, you see, this golf ball, type object kind of sitting on a tower in the distance. That is the Brandon radar, or KDGX. So if you were looking at some information somewhere, that would be the radar that you would use to see what's happening in central Mississippi. And then the Greenwood Springs radar is up around the Columbus area. It's really north of Columbus, kind of a little closer to the Aberdeen area. And that is the other radar that we use for central Mississippi. Of course, there, like I said, other radars you can see on the map that, cover different parts of Mississippi. But if you want to catch most of central Mississippi, the Greenwood Springs radar and the Brandon radar are the two that you would use to see this area. So again, radar is radio detection and ranging. And the basic premise for how the radar works is you have this beam that goes out. It hits objects. Different objects have a different scattering pattern, but it'll hit an object. And the same transmitter is also a receiver. So it shoots out the beam hits an object. The beam is dispersed in different directions, and it waits for kind of the beam to come back. And when it comes back, then we see a pattern, which is the reflectivity that shows up on our radar. So this happens at a really, fast process. Lots of different, things are coming and going, in a really short period of time that gives us what we see on reflectivity. In early radar, this is the technology. The beam goes out, the energy comes back, and then we see that there is something in the distance. So, of course, because the Earth is round, it is not flat. As the beam goes out, of course, the height of the beam will change. And so, sometimes you can hit, the beam, goes out at a short distance, and you can catch the center of some rain, you can catch the center of a storm, you can see the hail, you can see all these different things happening. If you take that same storm and you looked at it from maybe the Columbus radar that is hitting it at a maybe a higher elevation, then you may only see some rain or catch the top of that storm. So we do have to take into account that the Earth is not flat, and that as this beam goes out, that the height of the beam will change, and we will see different angles of different objects as we get a greater distance from the our central location. Um, and so okay, so um, we have something called a volume control pattern that kind of controls how much we see and how quickly we see it. In a radar, I mean, in rainfall mode, we will we like to see information a lot faster. Of course, we would like to see a greater picture, but we're looking for information to come to us in in a shorter time, and so we'll get a good amount of data, but it'll give it to us in either for somewhere between 4 and 6 minutes. We're in a clear air mode, which is sunny day. It'll take somewhere to 7 to 10 minutes to get us information, and we'll just get a chance to see a lot less data. It doesn't give us a full volume of information. And I may not have mentioned that in general. So yes, we get the beam to go out and it hits objects, but the beam goes up. It kind of rotates up. So it goes up and it spins, and then it goes up and it spins to give us a kind of a profile of what the environment looks like, to give us these pictures of this reflectivity. Let's see if it'll show. So this is to give you a rough idea, of the beam going out, and then the different levels where it's collecting data. So this is the one of the rainfall volume control patterns that we use. That'll give you a 6 minute scan. Here we have this 4 minute scan. So it's giving you data a lot quicker, but you can see that it gives you a few more elevations than the previous scan. And then we're in a clear air mode. It takes a little bit longer. The radar is going at a much slower pace. It actually probably gives the radar an opportunity to rest. So if we're in the weather, we've had rain for a number of good amount of time, a day or so, and the radar hasn't had an opportunity to go back to clear air mode. If we have a time we can take a break, we will give the radar a break. It is a motorized device, so it does have wear and tear on it as well. And then here is our other volume control pattern that is also clear air, that is a little bit shorter, and collects a few less elevations. Okay, so we will switch to Eric.
Hello, everybody. Let me see if I can share my screen here. And Christiane, are you seeing that?
Yes, it looks good.
Great. Thank you, Latrice. Just kind of picking up from where Latrice left off. She talked about the evolution of the radar. She mentioned the Doppler radar, and you probably hear that name a lot, Doppler, and I'm going to kind of talk a little bit about what that means. So generally speaking, when you think of the radar and you're watching it on the news or your favorite channel, social media, or whatever, you might when you see red, the color red, that kind of correlates with stronger storms, generally speaking, and that's the most well-known product that we have. You may have heard terms like the hook echo, and this is a image of of a hook echo here, which is associated with a usually or often is associated with a tornado, but it's a supercell thunderstorm. So I'm going to go a little bit more into how we can actually even better diagnose the tornado potential of a storm, or perhaps even see the tornado as well as I go forward here. And let me see if I can get my screen to move. There we go. So the Doppler effect, where does Doppler come into? So basically, one of the best ways, one of the best analogies that I like to use is for when a policeman is measuring speed from cars passing by. They use their radar systems are a Doppler system. It's using frequency changes to measure the speed of an object, basically. And the best way to sort of illustrate that is with something related to sound. So like when you hear an ambulance coming towards you, you'll notice that the pitch becomes higher and higher until it gets up to you. And then as the ambulance is going away, you'll notice that it kind of gets the pitch lower and lower and lower. Well, that change in the frequency shift is that's basically what's being measured whenever the beam goes out from the radar. It's bouncing the radar beam off of the objects, whether that be a raindrop, snowflake, a bug, whatever. Depending on what that frequency does when the energy comes back, we're able to determine the motion of these objects. And this is, I don't know if you can hear that or not, but that's a train. A train signal there. Christiana, were you able to hear that?
Yes, we heard it.
Okay, good. That's good. But the way, if you heard, let me do it one more time. You hear it's a high pitch, and then it gets lower. That's basically the shift that we're measuring. Okay, so with that in mind, so when we look at storms on the radar, so we see the traditional, the red colors and everything associated just with the pure reflectivity, or just straightforward energy being reflected back to the radar from the hydrometeors that are out there. We see that, but we also are able to look at the Doppler effect here, and this is how it looks when we're measuring motion. And we call it, and I'll say this is a radial motion, and what I mean is the radar, which in this case, this is our radar for our office down in Brandon, downtown Brandon. You can actually see it from the interstate if you happen to be passing by through there. It's like a big soccer ball. It's about 100 feet up or so. And what it's doing, so the beam is going out to this, you see this storm up here in to the northeast of Carthage, say roughly 60 miles away or so. And it's measuring the motion along that beam. So it's not necessarily going to measure the true velocity, but it's going to get everything that's along that radial, if that makes sense. And I'll kind of show you here a little bit more about that. But basically, what we're able to see, you see the reds are the motions going away from the radar, and the green, the cooler colors, the greens and blues, are motions towards the radar. So we're able to deduce a rotating storm here because of that. We're seeing motions towards, motions away, and of course, most bad weather rotates counterclockwise. Tornadoes, in particular, just about all of them are going to be rotating with that kind of direction. Not all of them, but most of them in the northern hemisphere. And so to illustrate that a little bit more, this is just kind of a pure radio motion, assuming that it's sampling everything the radar is. And like I mentioned before, you're seeing winds coming towards the cooler green colors, and the winds going away from the radar in these red colors. So in this particular example here, if the winds were coming out of the south, this is likely how it would look on your radar screen with just kind of a general south wind. And like it says here in this illustration, if the winds are, say, going, well, once again, if they're going from south to north, and let's say our radar beam is, like you see here, it's pointed that way, you're only going to be measuring that small component of that wind that's going to the north. And then if you're looking at a radio beam that goes this direction, and the winds are going from south to north, you're not going to see anything. That's what we call the zero isodop. That's this kind of a white color that you see right here, where the radar does not recognize any motion. But although technically there is wind that's coming from the south to north, I know that's a lot to kind of wrap your head around. It's not easy for us. We've been looking at it for years, but I just want to give you an idea that the radar is not, seeing every bit of motion out there, but it's got a good idea. And these are some examples of different storms around here that have occurred over the years. And when we put this in motion, we can kind of get an idea of, we loop the radar data to see if the storms are coming towards us and to see how they're changing as well. And in this particular case, you see a lot of red color. So you're seeing, and also you'll note that the radar viewing angle is actually this way. Storm motion is that way. So it's picking up some of the motion that's going in that direction, but it's not getting all of it. So we have to kind of make some deductions here about how things are actually rotating in real life, or how they're moving. And this is another example of the same storm. So the radar that you saw before was from Jackson, or the Brandon radar. This one's actually up at Columbus radar, which we actually we govern that one as well, up at Columbus Air Force Base. And that one's, to give you an idea, is up to the north of it. So it's seeing the storm from a different direction, and it's showing that the winds are going towards it. And that, because of that, it's got more blue and greens versus the red that you saw just a minute ago. So depending on where your radar is, you're going to get different colors, but they're all going to kind of give you an idea. We put the radars together basically to get a picture, a mosaic, if you will, of how the storm's behaving. And these are a little bit better examples of what might actually be tornadic storms. And you see this product, we call it storm relative velocity. So based on the motion of the storm, we're able to come up with a kind of a better idea of the rotation. So if we tell the radar what the storm motion is, it's able to give us a better idea of how the rotation is behaving, and you get a clearer picture. So what you see here on the left is the radar without knowing the storm motion. You can see that it's a little tougher to see exactly what's going on, but on the right, when we tell the radar the motion of the storm, all of a sudden it becomes clearer how the rotation is. And once again, we call this, the one on the right, we call that storm relative velocity information. And I show you that because it's really critical for when we're looking at tornadoes in particular. A few other products that we use, just to get some basic products. One's called Echo Tops. Basically, that's the taller the storm is, the stronger it usually is, more intense. Maybe the better chance that it's got hail. So that can be an important, especially for like aviation interests in particular. That can be an important product. It will look something like this, and you get an idea of. So in this particular case, you see kind of these orange colors. that tells you it's a thunderstorm with tops of over 40,000 feet. This is in the Hattiesburg area. So that represents a pretty strong storm, and definitely one for say aircraft to avoid. Another common product is one that based on algorithms that comes up with estimated hail size. So if it sees a storm that's got high reflectivity at way up in the sky where it's really cold, there's a good chance that there's hail with it. And this product will give you an idea of how big the maximum hail size could be. In this particular case, it's up to near 2 inches. Chances are it's going to be lower. The hail that's observed is going to be lower than what you see here. This is like an absolute maximum that would possibly be observed here near Purvis, Mississippi. And we definitely use that information when we're doing our warnings. We'll add this kind of information to the warnings. So we talked about the Doppler radar and how we determine velocity. Well, we've taken things recently to a new level with what we call dual polarization. And the difference with this, Latrice showed you earlier, she showed you with the basic radar principle, you just sent out one beam, and it was a horizontal pulse. The one that you see here, this kind of blue color, that's the standard radar beam energy that's going out and coming back, and basically sending really quick burst of energy out there at the speed of light. It's really quick stuff. But what we're doing now is also sending out this vertical beam as well. And what that does is allows us to determine the shapes of the objects that are out there, whether it's hydrometeors, like snow, hail, and rain, or biological targets like the bugs. It could be dust particles. And in a really extreme situation, if there's a tornado, it could be a piece of a house, tree, refrigerator, hopefully not, but it's measuring whatever's out there. And it's doing, it does a good job of giving you an idea of the shape of those objects. And I'll tell you the importance of that here as we go along, but I just mainly want you to get an idea of what we're sending out, this horizontal and the vertical beam, as you see here. And this is so the importance of the shape of the sizes. One thing and let me show you this again. One thing that's interesting that I didn't really appreciate until we started really learning about dual polarization radar is that the rain is actually a flat object. You would think of you think of rain as being the kind of the teardrop shape, but rain is actually I think what's the word, oblate or something like that. I think it's the word they use. It's actually kind of a flat object as it's coming down, believe it or not. Of course, hail is usually sometimes it can be uniform, spherical. A lot of times it's got appendages on it and little spikes and things like that. It's not uniform. Then you've got snow, like ice crystals, which can actually be more of a vertical shape. So based on that knowledge, the radar can kind of give us an idea of what kind of precipitation is out there. And just to illustrate this further, you can see here the different, it could be snow, rain, or hail. You got biological targets, differentiating between that and hydrometeorological targets. And then one thing that's really the use when dual polarization radar first came out, it was really more a matter of trying to determine the different precipitation types better. But as it turns out, we found out pretty quickly it's really good at seeing debris that's in the sky from tornadoes. and that's where the term tornado debris signature comes from. And it's taken our tornado warnings to a whole new level as far as being able to determine. We actually can confirm tornadoes now based on the information we're getting from the dual polarization radar. And so what's happening is, so if you have a uniform precipitation type, let's say like rain, which 98% of the time it's going to be mostly rain around here that's actually reaching the ground. If that, in that particular case, this is kind of a, this might be kind of a wintry type situation here. This is something called correlation coefficient. Basically, and as I mentioned before, you have the horizontal and the vertical beams that are going out. Well, if the horizontal beam is a lot different than the vertical beam, then you get low correlation coefficient values like you see here in these kind of yellow cooler colors that you see with this ring here. If it's if things are very uniform and both are the same, or we're getting the same values with each, we end up with these richer red colors, which indicate close to a 99 to 100% correlation. This tells us that there's uniform, if you look at this, uniform things falling from the sky. This ring right here that you see is actually the radar. As Latrice showed you earlier, the radar beam is getting higher in the sky as it goes from where the radar is farther out because of the Earth not being flat. And not to mention the fact that the radar beam is not going out straight; it's actually going out. The radar beam is actually going up at a slight angle as well. So when you put those together, what you're seeing here in this ring is actually where there's snow that's falling well up into the colder parts of the atmosphere, and as it's falling, it reaches this the melting level, and that's in this particular case maybe say 1,000, 2,000 feet up above the ground, and it's melting. And as it melts, you're getting a big distribution of different size drop sizes or precipitation sizes, and it's showing up as kind of this chaotic ring that you see here. And then as it falls even further, everything's melted into rain, and you end up with a back to being uniform. This is all rain. So this is just an example of what you can see with dual polarization. But going back to what I was saying about the tornadoes, this is where it really makes its money. And what I've got here is a example of a supercell thunderstorm I mentioned earlier. You see your hook echo here, and associated with that hook, in association with it, there's actually very, very, very intense rotation. Your winds are going away. So your radar is right over here, roughly. These are winds going away from the radar and winds going towards the radar. So you're seeing a strong rotation associated with that, indicative of a tornado. You're actually kind of seeing the tornado in this particular case because the storm is close enough that you can do that. Most of the time, the storms will be further away and you won't be able to see the details of the actual tornado, but in this case you can because it is so close to the radar. If it had been further away, you might have seen more of this broader rotation that's showing up. But here's the correlation coefficient that I just went over, the size distribution of things that are in the atmosphere. In this ring right here, that distribution is very chaotic. So you've got a very low correlation coefficient. And what's happening is you get debris in the atmosphere at different sizes. It's being thrown up by the tornado. And because of the chaotic spectrum of those sizes, you're getting a very low correlation coefficient. And this tells us, in combination with this reflectivity and this rotation, we're basically seeing, we confirm that there is in this particular case, probably a very strong tornado that is taking place. And based on how high that debris is getting thrown up into the atmosphere, we can actually tell how strong the tornado is as well. This is really important information that we put in the warnings, and gives people more confidence that, hey, there actually is a tornado that we're seeing, even without visual proof of it. So a few different, I'm going to quickly go through a few different storm types that we commonly observe. Most of the time in the summer, you'll see a what we call a single cell thunderstorm. These basically last for maybe up to a half an hour. They go up, the updraft goes up, and they come back down. They don't last long, but they can produce some pretty strong gusty winds, sometimes severe winds if it's very unstable. Wind is definitely the main concern with these, but also hail as well that comes down with them. In the case of when we have a little more wind shear, we may see clusters of storms like this, where the storms kind of build off of each other, and they can hang around for a little bit longer because of that. These can also produce a lot of wind and other different types of severe weather, including tornadoes as well. They would usually be brief tornadoes if they did occur with these kind of storms. The MCSs, these are larger complexes of storms we often get around Mississippi. These are organized systems that occur with cold fronts, and they look like this on radar. They last a lot longer, and they can have embedded tornadoes with them, depending on what the wind shear is like. And this is another example. In this particular case, there was actually a lot of or several tornadoes that occurred with this system. Lots of little circulations. These are very tricky to warn for. Unfortunately, we get them a lot around here, but you really have to be on your toes if you're going to see them on the radar, because they can spin up very quickly with these little strong convergence lines like you see there. Let's see. This is an example of an extreme wind, damaging wind situation of intense combination of bow echoes that was pushing through. This is just kind of a time series of one system going across, but it gives you an idea how things can change on the radar as that's moving through. And let's see, just another example. This is a squall line that we would associate with wind. On the radar, you'll often see behind the main line of storms, you often see kind of these sinking areas where the bluer color starts showing up. That represents wind that's coming down in behind the storms, represents the possibility of very strong winds coming in behind it. And this is a classic bow echo signature. If you ever hear the term bow echo, that's literally where the wind is literally bowing out the higher reflectivity that you see here. So this is usually indicative of very strong winds, assuming that you're unstable at the surface. Sometimes you can see these kind of signatures in the winter, but because it's so cold at the ground, this wind may not actually be reaching the ground. But if you're warm at the ground level, this is definitely a sign that you could be getting some really strong winds. If you're watching this on radar and you're looping it and say it's going off to the east there. Finally, last but not least, the supercell thunderstorm that we talked about earlier, that's definitely the one that is most noticeable on the radar for sure. It catches your eye the most quickly. And as meteorologists, Latrice and I will quickly note an issue if we see something like this on radar. We will definitely be concerned about severe weather and the possibility of tornadoes with something that looks like this on radar, where the rotation, the winds are wrapping around the updraft and creating this hook echo like you see here. So just quickly, some radar limitations. Latrice showed this a little bit earlier. The fact that the Earth is not flat and we're not able to see the lower levels of a storm that's farther away from the radar. Unfortunately, we can't have a radar every few miles. They're spread out, and some areas don't get the same coverage as others. You know, we would ideally we would love to have more radars that can see the storms, all the storms, in the same way. So when you're farther out, away from the radar, you can see here. This is an example in the bottom right where the storm. The second storm here is getting about half the resolution of this storm that's closer to the radar, and it's also being sampled higher up as well. So it's, you know, it's kind of a limitation for sure when you get further out in range from the radar. Another thing that can happen is what we call attenuation. That can be something as far as like mountains and things like that. The radar can't see through mountains. So out in the west, there's definitely a limitation as far as what they can see for storms that say develop on the other side of a mountain range. They may be seeing just the top of the storm in that particular case. Nearby, there may be man-made structures that cause problems. It could be water towers, just really tall buildings and things like that we have to work around. At one time, the radar in Brandon was here at the airport, and we had a problem with the trees on the ridge off to the east of the airport. Believe it or not, were causing problems of blocking the lowest scan. Those are the kind of things that they can be issues, and we have to, you know, we're knowledgeable of those, and we try to account for those, and we'll use other radars as well to try to help make up for that. Last thing I wanted to go over, just the future of radar. So I talked about the Doppler radar technology. I talked about dual polarization and the importance of that. Kind of the next step that we're taking, it's going to be a few years before we actually get the radar, but this phased array radar. And just to illustrate the conventional radar like we use now, and Latrice talked about, it does volume coverage patterns like this. It goes around lowest scan, next scan, next scan. And it takes about 5 to 10 minutes to complete a volume scan with that in mind, okay? Well, with the phased radar, you're going to see it actually can sample the storm all at one time. So instead of going each scan one at a time, it's actually able to take the scans all at once, which is really great because it can do it a lot faster, and you can get more of a 3D picture of the storm. So like in this particular case, this was a typhoon just that was sampled by a phased array radar. Is able to get this really nice, almost instantaneous 3D look of a storm, and it was able to show the different streamlines like you see here. It's able to figure out the winds better. So this will be some great technology, and we'll going forward. This is something that we look forward to getting. And let me see. I don't know if y'all can hear this, but it's a real quick video.
Yes, we can.
Great. Let's see.
One of the most promising tools on the horizon is phased array radar. Its rapid scanning ability lets NOAA researchers observe storms like never before. But will it be more useful for the National Weather Service? Will it result in earlier warnings for you? Let's find out what happens when forecasters go hands-on. The PREACE is the Phased Array Radar Innovative Sensing Experiment. We bring in forecasters from the National Weather Service, and we have them work cases, archive cases in simulated real time. And they issue warnings and update statements just as they would in the real world. So then that allows us to learn how the data is impacting their process, is it a benefit to them, does it increase their warning lead time. The past couple of years have been focused on tornadic storms that cause light to moderate damage. With current radar, the average warning lead time for these tornadoes is about 12 and a half minutes. What we found from 12 forecasters working events like that, their average lead time was 21 minutes. And so that suggests suggests that having this rapid update data, say on the order of a minute, really can make a difference in getting warning out and giving people time to respond. So far, so good. The experiment is set to continue annually and will cover all types of severe weather events. Learn more here and follow us. Okay, so these are the kind of things that we work on as meteorologists. Latrice and I have opportunities to actually participate in these kind of hazardous weather experiments, and that's something. As you saw there, phased array radar can actually help improve our lead time for detecting severe weather. So that's a good thing. And finally, and I'll hand it back off to Christiana. We have artificial intelligence. You hear about that with a lot of different sectors. The weather, it can definitely help a lot in the weather sector. As far as radar goes, probably the biggest aspect of our AI that we would benefit from is not necessarily the kind of stuff where it actually mimics human behavior, but more of this machine learning, deep learning section of AI, where basically we can connect dots. So, like if the radar it sees a particular rotation with a particular correlation coefficient at the same time, that can maybe indicate a better chance of a tornado or some kind of severe weather. That's the kind of information that we're working with. As human forecasters, meteorologists, we connect those dots in our brain, but the computers help us to obviously can speed up that whole process and give us information more quickly. So that's something that we're kind of looking at right now. There's not a whole lot of research right now as far as the radar stuff goes, but if you do a Google search, you can find a little bit, and this is just an example of where they're trying to match velocity patterns to make different inferences that can help us in the future. And with that, I think that's it. If y'all ever have more questions that can't be answered here, or we don't have time, there's our email address. Feel free to send that. It goes to our webmaster account, and everybody has access to that. Also on Twitter, where you can follow us, as you see there at NWS Jackson MS. We would love to hear from you. So, and that's it, Cristiano.
All right. Awesome. Thank you so much. So we have time for maybe one or two questions. Any questions that we don't get to, we will answer them when we send out the video. So does anyone have any questions? You can leave them in the chat or in the chat box, in the question and answer box. All right, we got a few comments coming in. LA Warren says, great information, weather systems and the usefulness and limitations of radar. It makes him wonder. Many people often ignore warnings and don't realize the severe, sometimes deadly threats. We're seeing the use of AI and immersive mixed reality, which is really cool, but probably costly to produce. I've seen examples of IMR on the Weather Channel. It's pretty compelling. Does NOAA or NWS produce these types of presentations, IMR presentations, of the region's increasingly hazardous storms?
I'm not real familiar with that myself. There may be, I will say that we're definitely in the infancy in the Weather Service with working with AI, and I'd have to follow up. And Latrice, do you have any information on that?
No, I'm not familiar with any. Not at this time, but we can, take a look and see if we can find something for you.
Yeah, I was gonna say we could, Christiana, if you want to, if we can get if they can give us their email and stuff, maybe we can follow up with that.
Gotcha.
That'd be great.
All righty. Any other questions from the audience? I have a question. So is Doppler radar used at all in long-term climate research?
So I will try to take this one. I don't know that we're using the radar for climate research, but there are some like environmental, ecological studies that are done using the radar. I remember one time there was a group that was studying the migration patterns of certain birds, and they were using the radar to keep track of bugs. So, like, you can get non-precipitation reflections in the radar. We usually will call it like ground clutter or something, but sometimes you can see, different things moving. And so they were keeping track of bugs on the radar because they were, following the migration pattern of a certain type of bird. So you'll have people that are doing those kind of like environmental related studies. I don't know that we're doing any long term like climate related studies directly from the radar though.
Okay. We have time for one more. Audience, do you have anything? Alrighty, so what are some common misconceptions that you notice in the public when it comes to Doppler radar? Are there any?
I would say maybe the most common thing to me is just just assuming that something that's like the red color on radar means severe. That's probably it's been that way for a long time. Somebody may oversimplify what they see on radar as being, oh, it's red, so it must be severe. Um, that's probably the biggest one I could think of. What do you think, Latrice? Um,
That's probably one of the bigger ones, the misconception of what they're actually seeing, um, in terms of intensity, directly related to the color
yeah,
scale.
yeah. For some reason, I'm having trouble. We get a lot of we get a lot of calls during weather. People are watching the radar, and they have their own. And in social media, people come on there and they give their. And I say the people, the general public, they may give their ideas of what's happening, but it's really, you really have to look at different aspects. The wind, the velocity, radial motions, the reflectivity, the environment. What's the environment doing? How unstable is it? It's not just the radar data. You have to put it all together. It's all part of a big puzzle when we try to figure out severe weather. So uh, for anybody to think that one particular item what represents severe weather on radar is kind of sometimes that's a common misconception.
Awesome. Thank you so much. So we are at time. It is now 3 o'clock. I want to remind you that there is an accompanying extension publication on Doppler radar. It will be on the Mississippi Alabama Sea Grant site on our resources page. I just left that link in the chat. We will also send out the recording of this video, and we'll have the answers and resources that were requested during this session in that email as well. Thank you all so much for joining us, and keep an eye out for the next Storm Tech webinar. Thank you.
Thank y'all.
Thank you.